Okay, now we'll start our last chapter of this chemistry crash course, chapter number 12, Organic Compounds. Organic chemistry is the study of carbon compounds. For anything to be considered an organic compound, it must contain carbon. See, organic compounds such as vegetable oil contain carbon and hydrogen and are not soluble in water. As you see in this picture here, you have vegetable oil being poured into a pitcher of water. And when this will settle out, the vegetable oil will be here on the top layer because it's not soluble in water, so it will form a film on top of the water. Alright, an organic compound will always have carbon and hydrogen atoms. There's no limit in how much they can have, but if carbon is found in the compound, it is considered to be organic. And they may also have other nonmetals like oxygen or phosphorus or nitrogen or even a halogen. Common products that you'll find organic compounds, gasoline, medicines, plastics, shampoos, perfumes. And we organize organic compounds by their functional groups. These are how atoms are bonded in a certain way. If they're bonded in a certain way, then they get particular names, like alcohols or aldehydes or ketones and so on. And compounds that are found in the same functional group have similar physical and chemical properties. Some properties of organic compounds. These organic compounds will typically have covalent bonds. They will have low melting and low boiling points. They will be very flammable and will undergo combustion, and they are not soluble in water. The picture we saw earlier, a sample of vegetable oil is a mixture of organic compounds that is not soluble in water. Now, many inorganic compounds have high melting and high boiling points. And inorganic compounds that are ionic are usually soluble in water, but most do not burn in the air. A very common example of a organic compound, propane, C3H8. Organic compound is used as a fuel, cookers and propane tanks, and so on. Sodium chloride, which is a salt, is an inorganic compound that's composed of sodium and chloride ion. Now we'll move on to representations of organic compounds. Now, hydrocarbons are organic compounds that only have carbon and hydrogen. That's why you have the name hydrocarbons. In organic molecules, each carbon can have 4 bonds, or up to 4 bonds. In methane, for example, CH4, you have 1 carbon atom, and it forms an octet by sharing its 4 valence electrons with 4 hydrogen atoms. And you see various ways to represent methane here. And even though they look very, very different, they all represent the same compound of methane. So for the one that's here in A, that's called the space-filling model. Letter number B, the ball and stick model, where the darker color would be carbon and the whites would be hydrogen. So 1 atom of carbon and 4 of hydrogen, so that's CH4. Letter C is where you have what's called a wedge dash model. The solid wedge like this is a 3-dimensional representation. This hydrogen atom here would be coming out of the screen, coming toward you, like a 3D movie would be. And if you have a bond that's dashed, like this one here, it is going behind the screen. For letter D, that is what's called an expanded structural formula. Solid lines represent individual bonds. And then for letter E, what's called the condensed structural formula. You are writing this basically without showing how all the things are bonded. So all 5 of these represent exactly the same compound, just in 5 separate ways. We'll talk a little bit more about methane, CH4. The expanded structural formula shows all of the atoms and all of the bonds connected to each atom. So again, you have the central carbon here, and then the 4 individual hydrogens, all bonded by single bonds. There's 1 line, that means it's a single bond. And again, the condensed structural formula, it shows the carbon atoms that are grouped with attached numbers of hydrogen atoms. So instead of writing it out like this, you're just writing, there's 1 carbon, 1 is understood, and then 4 hydrogens. So again, these are exactly the same thing. Just in some cases, it's easier to write it like this, and sometimes it's easier to represent how everything is bonded together. In methane, like we talked about before, carbon will form 4 covalent bonds to hydrogen. So this is considered to be a tetrahedral shape because it has 4 sides to it, and it has the bond angles of exactly 109 degrees. So if you were to take the ball and stick model here, the angles between these hydrogens are exactly 109 degrees. And the hydrocarbon is referred to as a saturated hydrocarbon when all of the bonds in the molecule are single bonds. Methane would be a good example of that. all the bonds that are found in a whole compound are all just single bonds. They're not double, they aren't triple, they're all individual single bonds. So that's considered to be saturated. All right, we'll talk about another organic compound, ethane, C2H6. Another tetrahedral carbon compound because it has four sides to it. It has three covalent bonds to hydrogen, and then one bond from a carbon to the other carbon, because there are two here. Again, these are the 5 ways to represent ethane. The space filling model here. The ball and stick model here. The 2 carbons here. And of course the whites are the hydrogen. So you have 3 covalent bonds to hydrogen from each carbon, and then the carbons are bonded together. The wedge and dash model. The structural or expanded structural formula. Again, 3 hydrogens, and then the 2 carbons bonded together, and then the condensed structural formula. And all 5 represent exactly the same things, just in different representations. All right, now we'll talk about a class of organic compounds called alkanes. These are formed when you have a continuous chain of carbon atoms. And they're named using a very particular system called the IUPAC, the International Union of Pure and Applied Chemistry system. There are certain rules and certain protocols that you have to follow in order to name these compounds properly. But a good indicator is they all end in the suffix ane, A-N-E. So methane, ethane, propane, all those are alkanes. If you get 5 or more carbons in a row, you start to use the Greek prefixes to indicate the name of the compound. This table here shows the number of carbon atoms that you would have in the compound, that compound's molecular formula, and then the condensed structural formula. And we'll talk about what these are here in a few minutes. So methane, CH4, ethane, C2H6, propane, C3H8, butane. Once you get to 5 or more, then you start to use the prefixes. Pence for penta for 5, like a pentagon has 5 sides to the shape. 6 would be hexa, 7 hept, 8 oct, 9 non, and then 10 dec. All right, I'll talk a little more about the condensed structural formula. In this type of formula, each carbon atom and its attached hydrogen atoms are written as a group. And a subscript will represent the number of hydrogen atoms that are bonded to each carbon atom. So for example here, expanded, it takes up a little more room, and this shows you individual bonds. But this, CH3, is exactly the same thing as this. C, and there's 3 hydrogens. 1, 2, 3. Same thing here. CH2, 1 carbon and 2 hydrogens. 1, 2. And then the 2 bonds that are left to be formed by this carbon. And this carbon still has one bond left to be filled. Same thing, just 2 different ways to write it. Right, on the table we just saw a few slides ago, you saw on the far right side the jagged lines. This is another way to represent formulas. This is called the line angle structural formula. And this shows a zigzag line in which carbon atoms are represented at the ends of each line. So for something like this, each point on that line, or each segment, is considered to have a carbon. So for this one, there would be 1, 2, 3, 4, 5, 6 carbons. This is how you would represent a hexane. The carbon atoms that are at the end of these structural formulas are bonded to 3 other hydrogen atoms, and the ones that are in the middle will be bonded to 2 hydrogen atoms. So going back to this image, propane, there's going to be 3 carbons, so 1, 2, 3. Butane, 1, 2, 3, 4. So every segment of the line represents a carbon being bonded to something. All right, now we'll talk about conformations of alkanes. Carbon atoms in the chains are connected by single carbon-carbon bonds and can rotate, so groups that are attached can move around more freely. And these can have different arrangements, and these arrangements are called conformations. So if you look at this compound here, this is the same thing as this. This methyl group here is able to actually spin around in the circle. That's why it's being shown rotating here. That can rotate and will form different types of conformations. And as they rotate around that single carbon-carbon bond, they will appear at different angles. Talk about butane next. C4H10 will rotate, but sometimes the CH3 groups line up in front of one another, and sometimes they're going to be on opposite ends of each other. There are multiple ways to write butane. Here is the expanded way to write butane. C4, then H10. Of course, all these lines individual or represent individual bonds. Condensed structural formula for butane can be written any number of these ways. These all represent the same compound. These are all C4H10, but in different arrangements, different conformations. That would be correct. Or it can branch like this, or it can branch like that, or that. So all of these represent exactly the same thing. Everything on this page is butane. Whether you write an expanded formula like this, a condensed formula like this, or the line angle formula. Alright, now I'll move on to what are called cycloalkanes. These are cyclic alkanes, and they will have two fewer hydrogen atoms than the open or the regular form would. And they're named by adding the prefix cyclo before the name. There's an example of propane, C3H8. This is the regular open air form. If you have cyclopropane, you have two less hydrogens. So instead of being H8, now you have H6, and they bond to each other. So you're forming a cyclic or a circle-shaped compound. That's why it's called cyclopropene. Instead of being open like this, it closes itself off. And by doing so, you're going to lose two hydrogens. Now here's some formulas and some representations of cycloalkanes. Cyclopropane, with the ball and stick model here. And what we just saw on the last slide here. If you're drawing the line angle formulas, you just write a standard triangle because it forms a triangular shaped compound. For cyclobutane, it has four sides to it, so it looks like a square. And the way you would draw it is literally a square for the line angle formula. Cyclopentane, penta means five. There's going to be five sides to it. You're drawing a pentagon. And cyclohexane, you have six sides, so you draw a hexagon. All of these are the same thing. All of these are the same thing. All of these are the same thing, and then all of these are the same thing. Multiple ways to represent exactly the same compound. Alright, now we'll talk about alkanes with substituents. When an alkane has four or more carbon atoms, the atoms can be arranged so that a side group called a branch or a substituent is attached to that carbon chain. And the first part we'll talk about are called structural isomers. These have the same molecular formula, but with a different arrangement of atoms, like we saw with butane a few minutes ago. We saw examples of the same compound, but written in multiple ways depending on how it was branched. So this is what we're talking about. So you still have the same number of atoms, but they're just bonded in a different order. So C4H10, butane, has two structural isomers, the straight chain, like this, where it's end to end to end, and then a branch chain, like this. Still C4H10, but that is branched here, and it's not branched up here. So exactly the same thing. Now substituents are atoms or groups of atoms that are attached to the carbon chain and include alkyl or halo groups. For alkyl groups, these are groups of carbon atoms that are attached to carbon chains, and they're named in the IUPAC system the ending YL or IL. And then halo substituents, these are halogen atoms that are attached to the carbon chain and are named with that IUPAC system by adding fluoro or chloro or bromo or iodo in front of the name. So for example, the formula name for methyl, the ending YL, methyl, CH3, and then ethyl here, propyl, because you have three, and then the formula name fluoro, chloro, bromo, and iodo. And these are some pretty common substituents that you'll find in naming chemical components. Now we'll talk about naming the haloalkanes. And the haloalkanes are alkanes with a halogen atom that replaces a hydrogen atom. And these are named by putting the substituents in alphabetical order. And you have the halo group numbered according to the carbon where it is attached to the alkane. For, say, this one, CH3 bonded to Cl. Well, that's a halogen, chlorine, so that would be chloromethane. That would be the IUPAC name. And the common name, methyl chloride. These all represent the same thing. CH3 bonded to CH2, and then bonded to bromine. Well, that's another halogen, so that would be bromoethane, or ethyl bromide. You have the halogen fluorine bonded here, so that would be fluoro, and it's attached to the second carbon in this chain. That's why it's 2-fluoropropane, and propane because it's three of these groups. It can also be called isopropyl fluoride because the fluorine is isolated. But again, that name and that name represent the same compound. All right, now we'll talk about melting and boiling points. Alkanes have the lowest melting and lowest boiling points of organic compounds, and they only have the non-polar bonds of carbon-carbon and carbon-hydrogen. The alkanes will also only exhibit weak dispersion forces in the solid and liquid states. And the longer the chain is of the alkane, the higher the boiling point gets. And if you think about it, it just makes sense. the more bonds there are, the more heat will be needed to break up those bonds. So the boiling point has to go up as the size of the compound gets higher. So for example, methane is only 1 carbon and 4 hydrogen atoms here. So its boiling point is negative 164 Celsius. If you get a little bit bigger, ethane, more bonds are involved, so it's a larger structure. So now the boiling point goes up to negative 89 Celsius. Getting a little bit bigger, propane, boiling point is now up to negative 42 Celsius. Butane, getting bigger, 0.5 degrees Celsius. And then pentane, boiling point is now 36 degrees Celsius. Pentane is much larger than, say, methane. So as the size increases of the alkane, the boiling point will increase. Now for branched alkanes, these will have a lower boiling point than the straight chain version of it. These tend to be more compact, therefore reducing the points of contact between the molecules. And they do not have linear shapes and cannot line up close to one another. So as you become more branched with an alkane, the boiling point decreases. So for this one, hexane, there's going to be 6 carbons all in a row, or 6 carbon groups all in a row. Its boiling point will be 69 degrees Celsius. When it starts to branch, you have 3-methylpentane. Boiling point is now 63 degrees Celsius, so you're going down. And then here, 2,3-dimethylbutane. Boiling point is now 58 degrees Celsius. These all represent the same number of carbons in the compound. So for hexane, there are 6. 1, 2, 3, 4, 5, 6. For this compound, 1, 2, 3, 4, 5, 6. And for this one, 1, 2, 3, 4, 5, 6. So the number of carbons in all 3 of these examples are exactly the same. But because it's becoming more and more branched, the boiling point will go down. For cycloalkanes, these will have a higher boiling point than the straight chain version of the same number of carbon atoms. And these have limited rotation of carbon bonds. They tend to maintain a very rigid structure, so they can easily be stacked closely together, which gives them many points of contact and attractions to each other. So here you can compare the boiling points of straight chain alkanes and branch alkanes and cycloalkanes. All these examples here have 5 carbons in the compound. So everything in this table has a compound that has 5 carbons in it. When it's a single end-to-end form, the straight chain form, it would be called pentane, a boiling point of 36 degrees Celsius. If it starts to branch, 28 degrees Celsius. If it becomes more branched, it becomes even lower, 10 degrees Celsius. And if it's a cyclic alkane, 49 degrees Celsius. So the cyclic version will have a higher boiling point than the straight chain version. Alright, now we'll talk about combustion of alkanes. The carbon-to-carbon single bonds in alkanes are kind of difficult to break, which makes them the least reactive family of the organic compounds. But alkanes will burn readily in oxygen to produce energy and water and carbon dioxide. So here's that generic equation. An alkane gas plus oxygen with heat added to it will give you carbon dioxide as a product, water, and energy. Alright, methane is a common natural gas that's used to cook food and also to heat homes. And the equation for the combustion of methane, CH4, is written here. CH4 gas plus oxygen added together and then heated will give you carbon dioxide and water and energy. And another alkane, propane, commonly found in portable heaters and barbecue cookers. And here's the equation for its combustion. Propane plus oxygen heated will give you carbon dioxide, water, and energy. Alright, now we'll talk about the solubility and the density of alkanes. Alkanes in general will be nonpolar. They'll be insoluble in water. They'll be less dense than water. They'll be flammable in the air. And it's something very commonly found in crude oil. Just like the example we talked about at the beginning of the chapter with the vegetable oil. It will float to the top of the water and form that film on top of the water. It's the same thing when you have an oil spill in the ocean. The oil will, because it's less dense than water, it will float to the top of the water and forming that film on the surface of the ocean. Alright, now we'll move on to alkenes and alkynes. Ethene, or commonly called acetylene, commonly used in welding, because it reacts with oxygen to produce flames with a temperature in the range of over 3,000 degrees Celsius. And the big difference between alkanes and alkenes and alkynes is the number of carbon bonds that are formed. Whenever you have a double bond between carbon and carbon, you have an alkene. If you have a triple bond, like you have here, that'd be an alkyne. Alright, first one we'll talk about, ethene, C2H4, commonly called ethylene, is an important hormone that's found in plants because it helps the ripening of fruits. And like you see in this picture, you have a very large number of bananas. Ethylene will help break down cellulose, which is a complex sugar in plants, which causes the flowers to wilt and then the leaves from trees to fall. Alright, naming alkanes and alkenes and alkynes. Now the rules for naming alkenes and alkynes is very, very similar to the process for alkanes, but you are replacing the ending with "ene" and "ine" instead of A and E. So for example, ethane, these are all single bonds here, but if you have a double bond between the carbons, it's now ethene. If you have a triple bond, ethyne. The same thing with the line formulas. If you have a double bond, you write a second line. If you have triple bond, you write 3 lines. But all 3 of these represent the same formula. All 3 of these represent the same formula. Then all 3 of these represent the same formula. All right, a guide to naming alkenes and alkynes. For one, you name the longest carbon chain that contains a double or triple bond. The double or triple bond is assumed to be the first bond between carbon 1 and carbon 2. Step number 2, you number the carbon chain starting from the end near the double or triple bond. Then you give, or step number 3, you give the location and name of each substituent in alphabetical order and as a prefix to the alkene or alkyne name. For example, we'll go over naming the cycloalkene. It's a cyclic compound, so it's going to form a circle as an alkene because there's a double bond here. So what you do is you assume that the double bond is between the first and second carbon. So when you're naming this overall compound, you know it's going to be a cyclic compound, so cyclo is going to have to be in the name. It has 5 carbons, it has to be penta, because if you see a double bond, it's going to be a pentene, so it's going to be cyclopentene. But then you have to factor in how to name this. You always start at the double bond or triple bond, and you want to give this location with the lowest possible number. So this is assuming that's the first carbon, 1, 2, 3. That'd be 3 methyl cyclopentene. If you were to start here and go the other way, 1, 2, 3, 4, 5. 5 is a higher number than 3, so you always want to give the lowest possible numbers when naming substituents for a compound. And now we'll talk about cis and trans isomers. When you have an alkene, the double bond is rigid and does not rotate, and so it holds attached groups in very fixed positions. So this will form 2 geometric isomers called cis and trans. It just depends on where everything is located in relation to that double bond. And when you're naming these compounds, you must include cis or trans as a way to reflect the structure of that compound. So cis and trans isomers will have different physical and different chemical properties because they are arranged differently. Even though you have the same numbers of atoms present, because of their arrangement, they may have different traits to them. These types of isomers cannot occur when 2 groups are on the same one of the carbons. And so comparing these 2 here, these are both 2 butene. This is cis, this is trans. Cis means they're on the same side of the carbon or the double bond. Trans means that they're on the opposite side. These 2 here, same side, and one up here, one down here, opposite sides. In the cis isomer, the alkyl groups are attached to the same side of the double bond, and the hydrogen atoms are on the other side. In a trans isomer, the groups and H or hydrogen atoms are on opposite sides of the double bond. So some more examples here. All of this here is 3-hexene. These groups are on the same side. That'd be a cis 3-hexene. They're on opposite sides, like here and here. That's trans isomer. These all represent exactly the same numbers of hydrogens, the same number of carbons, but how they're arranged will impact how they're written in the structural formula, and also their chemical and physical properties. So if you were just to name this example as just 3-hexene, that'd be wrong. It is cis 3-hexene. If you were to drop off the name trans for this compound, name would be wrong. The proper name for this compound here is trans 3-hexene, not just 3-hexene. All right, addition reactions. In alkenes and alkynes, the double and triple bonds are going to be very reactive and undergo hydrogenation, the addition of hydrogen bonds, and hydration, addition of hydrogen and hydroxide to carbons in the double or triple bond. They'll undergo polymerization at high temperatures and high pressure, and these also be easily broken in providing electrons to form new bonds. So for examples, hydrogenation, you have an alkene plus hydrogen. We end up getting is an alkane. For hydration, you have an alkene plus water, and what we end up getting is a product of an alcohol. And for polymerization, you have an alkene as a reactant, and what you end up with after high pressure and high temperature, you get a polymer. So we'll talk about hydrogenation first. In hydrogenation, you get hydrogen atoms that are added to the carbon atoms of a double bond or a triple bond. And then you have a catalyst such as platinum or nickel that are used to increase the speed of the reaction. So over here, you're starting off with an alkene, then you're adding hydrogen atoms, the catalyst of platinum. You end up getting a product of an alkane. For this one, you're starting with an alkyne, adding hydrogen. Nickel is used as the catalyst. You end up getting a product of an alkane. So these hydrogen atoms will take the place of one of these bonds. So you start off with a double bond here, end up with all singles here. Start off with a triple bond here, you end up with all singles here. We'll talk briefly about Markovnikov's rule. When water adds to a double bond in an asymmetrical alkene, you have two possible products. So this rule states that the hydrogen from the water will attach to the carbon that has the greatest number of hydrogen atoms, and the hydroxide part of the water adds to the more substituted carbon atom. Alright, now we'll talk about polymerization. A polymer is just a large molecule that has many individual segments called monomers. Poly means more than one. So individual units that are repeating would be a monomer. But you get them end to end to end, then you get a lot of those monomers, so it's a polymer. And many of these polymers are produced by addition reactions of alkenes. And probably the best example of a polymer would be plastics. So plastics, things that you'll find in non-stick pads or plastic cups, rain gear, carpeting, and so on. Some common examples here: the polystyrene for styrofoam cup, saran wrap, as a formal name here, and then Teflon. All those are examples of. Alright, in medicine, you'll find synthetic polymers that are used to replace damaged body parts like artificial hips, artificial joints, pacemakers, teeth, heart valves, blood vessels. So all those are or contain different types of polymers. Alright, many of these synthetic polymers are made by the addition reactions of small alkene monomers. So you usually need for this reaction to happen is you need to have a catalyst, you need to have a high temperature, and a high pressure, usually over 1,000 atmospheres. So in each addition reaction, the polymer will grow longer as each monomer is added to the end. So a polymer is just a monomer end after end after end. It's a repeating unit. Now a polymer may contain as many as 1,000 monomers. An example here, polyethylene is a polymer that is made from ethylene monomers and is used such as plastic bottles, film, plastic dinnerware. And it comes in two different forms: low density polyethylene and then high density polyethylene. The low density, or the LDPE, is very flexible, breakable, less dense, and is more branched than the high density form. The high density form is going to be much stronger and a lot more dense than the low density version, and it melts at a higher temperature than LDPE. This table has several alkene monomers that are used to produce some synthetic polymers. Here are the monomers listed here. That will be written out in the structural formula and some common uses: plastic bottles, shopping bags, plastic pipes, carpets, artificial joints, and so on, Teflon, plastic coffee cups. So these are some very common examples of polymers here. Now the alkane-like nature of these plastic synthetic polymers makes them unreactive. So that leads to some problems. Because they are unreactive, they don't decompose all that easily. They're not biodegradable, so they are a pretty large contributor to pollution, both in the oceans and on land. So for all the good that they offer, there's a downside to them also. Now we'll talk about benzene, which is an aromatic compound. Now an aromatic compound has a ring of 6 carbon atoms, each bonded to one hydrogen atom. This will give you a flat ring structure drawn with 3 alternating double bonds. And benzene will be represented by 2 structures because the electrons are shared equally among all the carbon atoms. Now, benzene is also represented by a line angle structural formula using a circle inside the center instead of the alternating double bonds. You can write benzene either this way or this way because these double bonds are able to kind of shift because the electrons are shared equally. So benzene can be represented like this with the ball and stick model, or like this, but it's commonly written like this. You have the hexagon shape because it is a ring of 6 carbons, and then the circle in the middle to represent these shifting double bonds. Some other common examples of aromatic compounds that we use for flavoring, such as in cooking. Tarragon is one here. Thyme is another one. Anise is another one. These are all examples of aromatic compounds. Some properties of aromatic compounds. The flat symmetrical structure of benzene allows for interactions between these cyclic structures, which contributes to the higher melting points and the higher boiling points of benzene and all of its other derivatives. There's a table with various compounds and then their melting points. Benzene, melting point of 6 degrees Celsius compared to these other versions. Now, aromatic compounds are going to be less dense than water, but usually they are more dense than other hydrocarbons, but they're still less dense than water. Halogenated benzene compounds will be denser than water. Aromatic hydrocarbons are insoluble in water and are used as solvents for other organic compounds. And only aromatic compounds containing a strong polar functional group, such as a hydroxide or COOH, will be somewhat soluble in water. And benzene and other types of aromatic compounds are resistant to reactions that break up the aromatic system. Although they are flammable, but they tend to keep their shape pretty well. Alright, that brings us to the end of Chapter 12 and the end of this series of videos on a crash course in chemistry. I hope you've enjoyed it. I hope you feel that you've learned something from it. So thank you for watching. Thank you for watching our newest video on our crash course in chemistry. And don't forget to subscribe to this channel so you can be notified of when our new videos are posted.